Hi guys, so in the last videos we have already learned what is stress and strain, how to calculate the deflection when loads are provided in any member. So in this video, before starting the new lesson, let's have a problem based on the previous lesson where we have learned to calculate the deflection. How? By Hooke's formula, that is your deflection is equal to PL by AE. You know that P is the applied load on the length L, and here is the cross section, and is the modulus of elasticity. So here you have to calculate what is the total deflection in this system. So in those cases, this type of questions have come many times in ESE. This is also come in GATE in terms of or in the form of MCQ. So to calculate the total deflection in this type of problem, first you need to just break this. Okay, so first part is your this one, here length is L, and here the overall cross section is constant. Okay, so for each part, let's say here the cross section is A, here is also A, and here is also A. So the first part is L, cross section A, and load is, always start to draw this free body diagram from outside. So here load is 5P. Due to this external load, what should be the internal reaction? Obviously, to maintain equilibrium, it should be 5P. Okay, then draw the adjacent part. Again, this is your 2L total length. Okay, and due to this internal reaction, an opposite internal reaction will also develop here, that is your 5P. Now come to external load, that is your 8P, but direction is in this direction. This is your 8P. So overall or resultant force is acting like this, or in terms of nature of the force, it is acting as a compressive force, and the magnitude is 5 minus 8P, that is your 3P. Minus means the compressive in nature. So similarly, here is also a compressive force, 3P will act as a reaction. Again, similarly, draw the free body diagram of this last part, and here it is like this. The total length is L, and due to this 3P, and internal reaction force is acting here 3P. Now come to your 2P. Okay, so here 2P is acting outward. Okay, and overall resultant is P, and this is acting say towards, overall reaction is P, and this is acting your inward. Okay, here. So similarly, here also an inward force should act with magnitude P to maintain the equilibrium. That means this problem is actually fundamentally wrong. This force should not be 5P, rather it should be P. Okay, now you can calculate the total deflection for each term. Here this is under tension, and total deflection is your 5P. L is length is L divided by AE. Here the deflection is negative. Why? This is under compressive load, so this is your minus. Load is 3P into length is 12 divided by AE. Let's say here the cross sectional area was like this, or let's say 2A. In that case, this should be 2A. Okay, but it is not here, so we will remove this 2. And what about this last one? This is also under compressive load. Okay, so minus, load is P, length is L divided by AE. So simply to get total deflection, you have to sum up all these and you will get your answer. Okay, so this is a very common type of problem which comes in your competitive examination from this Hooke's law or from this formula, application of this formula. Okay, so if you have any other problem or difficulties, please let me know in the comment. So let's start the new lesson, which is in this lesson we learn how to calculate the stress and strain due to self weight. So in the previous lesson you have learned, if this is a bar, we have applied an external load, let's say P, and we have calculated what is the internal stress or strain and what is the deflection, okay, due to this external force. Now let's say this is a bar and this is very long, so obviously its self weight will be, definitely it cannot be ignored. So we need to calculate the stress and your strain and also the deflection due to its self weight. Okay, so this is the reason why we should learn the how to calculate the stress and strain due to self weight. So let's start. First assume any bar, let's say this one, the total length is L and cross section is your A, and it is constant throughout the length. That means this is a prismatic section, okay, prismatic bar. Okay, so area is constant throughout this length, and the unit weight per, or the density or unit weight per volume, per unit volume is rho. Okay, so rho is the unit weight per volume, or weight, this is actually wrong, we should not say unit weight per unit volume, it should be weight per unit volume. Okay, so this is rho. Now we have to calculate what is the stress coming. So can you tell me where the stress would maximum? Obviously here the strain, there is no load due to your self weight, 0, but here there is load is coming due to this portion. Again here load is coming due to all this portion. So obviously the maximum stress will come here at this built up end. Okay, so what is the maximum stress? Simply the total weight of this bar is, your volume is cross sectional area into length. Now simply multiply this with your density or rho. This is your total weight or P, and this is acting over area is your A, because constant area, this is a prismatic bar. Okay, so what is your stress? To calculate your stress you simply need to P by A, or simply A is cancelled out here and you get your rho into L. This is your maximum stress which is coming at your built up end. Okay, now if I ask you to calculate what should be the stress at any middle, simply you can calculate it. Let's say we have to find here what is the stress. Simply what you need to know, what is the length of this stretch. Let's say, again draw it clearly. Let's say we have to calculate the stress here, and this is at the depth of x from bottom. Okay, so what is the weight of this portion? Because the weight of this portion is acting in this section. Okay, and it is, weight is your rho is the density, volume is A into x, and cross sectional area is A. So stress is simply rho into x. So here you can see maximum is rho L, and at any section it is rho x. So stress is a function of your length, or stress is varying linearly. Clear? Now consider your in this bar there is both your, what should I say, load is acting and the self weight is also acting. Consider this bar. Okay, here load, external load is also acting. This is P, this is P, and the length is L, cross section A, density is rho. Now you have to calculate the deflection, or you have to find out the relation between this cross-sectional area and external load and the internal stress. Internal stress, let's say we are allowed to go up to stress sigma working. You have already learned what is working stress. Okay, so now we have to find what is the relation between this cross-sectional area and this working stress. Clear? You have already learned that sigma max comes at the build-up end, and this is your rho L due to your internal or self weight, and due to external load this is P by A. P is the external load and A is the cross-sectional area. Now what is the value of this W or the sigma max? Sorry, not W. Sigma max is your sigma working. Okay, so if I have to find the cross-sectional area required for a particular length of bar when external load P is applied, we can rearrange it like this: P by A is equal to sigma W minus rho L, or we can write that required cross-sectional area is equal to the applied load P divided by the allowable stress or sigma W minus rho L. So here you can see there are a lot of implication of this equation. What are these? Well, the very first one is when the length increase, simply this term increase, agree, and the whole denominator decrease. Okay, and when this whole denominator decrease, that means your requirement of cross-sectional area increase. So more is the length of the bar, more is the requirement of your cross-sectional area. Now let's say somehow the length is such that your sigma W become equals to rho into L. Okay, so in that case what will happen? The denominator will simply become 0, and cross-sectional requirement is, what is area required is P by 0, and that is nothing but tends to infinite. So it is not possible to apply any load when your length is sigma W by rho. If you know the working stress and if you know the density of the material, then you can find out the maximum length up to which you can go without applying any load. Clear? So this equation have a very big implication. So now you can ask me, that means we should not apply any load for a larger length? No, in that case you have to apply a variable cross section like this, or the non-prismatic section. Okay, this is the reason why we use non-prismatic section when we apply load in these cases. Okay, so you have got the reason behind it. Now you have to find the deflection which actually occurs due to this self weight. So we have to find it for both the cases. First one is when the section is prismatic, and the second case is when the section is non-prismatic. Clear? So first find out this deflection due to self weight in case of a prismatic bar. Let's consider a prismatic bar. Let's say this one. This is the prismatic bar of length L, and cross section is A throughout the section, and the density of the material is, let's say this is rho. Okay, and now you have to find the deflection due to self weight. There is no external load. Okay, so at any distance from the bottom, let's say X, consider any cross section. So what is the load is being applied here? The load due to this portion. Clear? And consider a very small, which is tends to 0, very small zone of thickness or length dx, where dx very small, which tends to almost 0. Okay, so we can say here that there is no extra load is acting, only load due to this region is acting on this length or dx. Okay, so what is the stress acting here on this dx or in this cross section? You have already learned this is your rho into x, sigma x is equal to rho x. Okay, now from Hooke's law you know that your stress is equal to strain into modulus of elasticity, where strain is nothing but deflection per unit length. Okay, so total deflection can be written as sigma into L divided by E. So at this section, for this dx length, what should be the your deflection? It should be very small, let's say d delta, and this is nothing but force. From this equation, sigma is rho x. Okay, sigma is rho x, length is dx, very small amount of length, divided by your modulus of elasticity. This is constant throughout the length. Now to get total deflection, you need to integrate this small deflection from 0 to L, or due to the load acting from bottom to the top. Okay, let's integrate it. So integrate this one, we get rho x into dx divided by E, and this need to be done from length 0 to your length L. Okay, from that we get rho into L square by 2E. This is the deflection due to self weight in case of a prismatic bar with the given condition like this. Cross sectional area is A, your density is rho, length is L. Clear? So again, from this equation or from this formula, tons of questions may come in your EAC or GATE. You can check this in previous question, where you will get that directly these formulas have been asked. What is the deflection in case of a prismatic bar due to its self weight? Simply this formula has been given in the options. Okay, so this is time to go forward, and now we will learn how to calculate deflection due to self weight in case of a non-prismatic bar. So what is non-prismatic bar? Where cross section varies with the length. Let's say this is the non-prismatic bar, the length is L, and cross section looks like this, a circular cross section. At the very top, this is D, or diameter is D, and it varies linearly. So at any depth, let's say from bottom this is x, the diameter should be, what is the diameter? D dash is equal to, simply from linear interpolation you can say this is D into x by L. When x is 0, this is 0. When x is L, this is D. Okay, so now we have to find what is the deflection due to its self weight. Let's calculate it. So at very first, what is the force acting here? The force is acting here in this cross section is the weight due to this portion. What is the weight? Simply cross sectional area of the base into the height divided by 3. This is the formula of any conical section. So what is the stress acting here? Simply divided this with the cross section A, and it is coming, sorry, you have to multiply this with the density only. In that case you will get the weight. Then we are dividing with the cross section, and it is coming as your rho x divided by 3. This is the acting stress at any section which is at distance of x from the bottom, and we are defining this as sigma x. Clear? Now from Hooke's law you know that stress is equal to strain into your modulus of elasticity, or delta per unit length into modulus of elasticity. From that you get deflection is equal to sigma into L divided by your E. Okay, so at this distance consider a very small thickness which is dx. Again, just like the previous cases, here dx is so small that it tends to 0. So you can assume that this section acts like a prismatic section. So for prismatic section we apply delta is equal to sigma L by E, and sigma here is your rho x divided by 3, and L is your dx divided by E, and this delta due to this very small thickness or small length can be defined as d delta. Okay, so to get the total deflection due to the self weight, simply just like the previous cases, you need to integrate this from 0 to L, and you will get as rho by 3e into integration of 0 to L of x into dx, or rho L square divided by your 6e. So this is the again formula which directly asked in your question in your exam, that what is the deflection due to self weight if these conditions are met, or the cross section is circular, diameter is d, and the total length is L, like this. So you have already learned how to calculate basically this deflection. Okay, so even now if a circular, instead of circular you are given a square cross section which varies linearly like this, you can find this deflection also. That's all. We will meet again in another videos. Till then, please study with these videos and the available textbook to you. If you have any doubt regarding any of this topic or any question, please let me know in the comment section.